Welcome! In this problem walkthrough, we'll be tackling LeetCode problem number 1419, minimum number of frogs croaking. This is a fascinating problem that challenges us to simulate and validate sequences of events while optimizing resource usage. Let's dive in and explore how we can solve this step by step. The problem asks us to determine the minimum number of frogs required to produce a sequence of sounds represented by the string croak of frogs. Each frog can only produce the sequence croak in the exact order of its characters, C, R, O, and K. A frog must complete one full croak before starting another. If the string cannot be formed by valid croaking sequences, we return -1. For the input, we are given a single string made up of the characters C, R, O, and K, with a length ranging from 1 to 100,000. The output is an integer representing the minimum number of frogs required or -1 if the sequence is invalid. Let's now explore some examples to better understand the problem. In the first example, if the input string is croak, the output is 1. This is because the sequence can be produced by just one frog. The frog completes the first croak entirely before starting the second croak. Since only one frog is active at any given time, the minimum number of frogs required is 1. On the other hand, if the input is croak, the output is 2. Here, 2 frogs are needed. The first frog begins the sequence, but the second frog must step in to start its croak while the first frog is still finishing its own. Thus, there are 2 overlapping croaks, requiring 2 frogs. Additionally, in the second example with croak, frog 1 completes the first croak, while frog 2 produces the second croak. This overlapping behavior makes it clear that 2 frogs are the minimum needed. Now, consider the third example where the input is croak. The output here is -1 because the sequence is invalid. The second croak is incomplete, as it's missing the final K. Since a valid croak must include all 5 characters in order, missing any character means the sequence cannot be formed correctly, and the function returns -1. Finally, in the fourth example, if the input is croak, the output is also -1. This sequence is invalid because there is an extra C that does not have a corresponding complete croak. Each C must eventually lead to a valid full sequence croak, and here that condition is not met. To summarize, the problem requires us to carefully track the state of each croaking frog and ensure that each croak is valid and complete. If any part of the sequence is unmatched or out of order, the function should return -1. These constraints help us identify edge cases, such as overlapping sequences, missing characters, or unmatched extras, ensuring our solution accounts for all possibilities. To tackle this problem, we can first consider a brute force approach by simulating each frog individually as it progresses through the string. The idea here is to assign every C in the string to a new frog, and then track that frog's progress through the croaking sequence C, R, O, K. As each frog completes the word croak, it is removed from our tracking, and we keep count of how many frogs are simultaneously croaking at any given time. However, this solution becomes inefficient for large strings. The time complexity is quadratic, n squared, because we are constantly updating the states of all active frogs, and the space complexity is linear, n, since we need to track every frog's state. While this approach is intuitive, managing the state of individual frogs quickly becomes cumbersome and impractical, particularly for long inputs with numerous overlapping croaks. A more efficient strategy involves tracking the counts of characters in the sequence rather than simulating individual frogs. The key observation is that the characters C, R, O, and K must appear in the specific order of the word croak. By maintaining counters for these characters, we can ensure that the sequence remains valid. For example, the count of C must be at least as large as R must be at least as large as O, and so on. As we process each character in the string, we increment the corresponding counter. If a K is encountered, meaning a croak is completed, we decrement all the counters to signal the reset of that frog sequence. Throughout the process, we track the maximum number of active C characters, as this directly represents the minimum number of frogs needed. This approach is highly efficient, with a time complexity of n and a space complexity of 1, as it only requires a fixed number of counters. An alternative to the fixed counters approach is to use a hash map to track the counts of characters at each stage. This method essentially replicates the logic of the optimized approach, but instead of using individual variables for each character, we use a dictionary. While this offers conceptual flexibility, it introduces additional overhead due to dictionary operations. For this reason, the fixed counters approach remains the more efficient choice. The optimized strategy focuses on maintaining the correct sequential order of characters, ensuring that each croak is valid. By observing that each completed croak allows a frog to start over, we can minimize the number of frogs by simply tracking the maximum number of simultaneous C characters. This insight simplifies the problem significantly, avoids managing individual frogs, and leads to a linear time solution. While the hash map variant is slightly less efficient, it could be useful in scenarios where greater flexibility is required. The optimized approach was chosen because it strikes the perfect balance between simplicity, efficiency, and robustness. By focusing on character counts and ensuring the sequence remains valid, we achieve a solution that is both elegant and highly performant. The time complexity is O(n), as we process each character in the input string exactly once, and the space complexity is O(1), since we only use a small, fixed set of counters regardless of the string length. This makes the solution scalable to very large inputs. Compared to the brute force method, which is both slow and memory intensive, the optimized approach is significantly faster and easier to implement. It is the most practical and effective strategy for solving the problem, making it the clear choice for this task. In this problem, we need to determine the minimum number of frogs required to simultaneously croak the word croak in sequence, given a string that represents overlapping croaks. Each frog can only croak in the specific order of C, R, O, and finally K, and it must complete the sequence before starting again. If the input string is invalid, for example, if characters are out of order or incomplete, we should return -1. To begin solving this, the first step is to validate the input. We check if the input string is empty, as this would mean no valid croaks are possible, and the result would be -1. Additionally, we ensure that the total number of C, R, O, and K characters in the string is equal. If not, it would be impossible to complete the word croak, so we would return -1 in this case as well. The next step involves defining the croak stages. Each character in the word croak corresponds to a specific stage in the sequence. For example, C represents stage 0, R represents stage 1, O is stage 2, A is stage 3, and K is stage 4. This mapping allows us to systematically track the progress of each frog as it croaks through the sequence. To implement this, we use an array called stages of size 5, initialized with zeros. This array keeps track of the number of frogs at each stage of the croak sequence. For instance, stages 0 represents the number of frogs currently at the C stage, while stages 1 counts the frogs at the R stage, and so on. This approach enables us to efficiently manage the progress of multiple frogs as they move through the stages. To process the input string, we iterate through each character and update the stages accordingly. When we encounter C, we increment stages 0, indicating that a new frog has started croaking. For subsequent characters like R, O, and K, we check if there are frogs in the previous stage to advance forward. For example, when processing R, we ensure that stages 0 is greater than 0. If it is, we decrement stages 0 to indicate a frog has left stage 0, and increment stages 1 to move that frog into stage 1. If no frog is available in the previous stage, the sequence is invalid, and we return -1. For the final character K, we decrement stages 4 to signify that a frog has completed its croak. Throughout this process, we also track the maximum number of frogs croaking simultaneously by summing the values in stages after each iteration. At the end of the string, we ensure that all frogs have completed their croaks by verifying that all stages except stages 0 are 0. If any stage is non-zero, it means a frog's croak is incomplete, and we should return -1. The problem revolves around the dependency between the characters in the word croak. Since the sequence is strictly linear, each character depends on the one that came before it. This ensures that the stages must progress in a specific order. Using an array to track the stages allows us to efficiently simulate the progress of all frogs without explicitly managing each one individually. The maximum number of frogs croaking at the same time can be determined by observing when the sum of the stages array reaches its peak during the iteration. This peak value gives us the answer. For data structures, we primarily rely on the stages array, which groups frogs by their current state in the croak sequence. This simplifies the problem significantly. Some important edge cases to consider include invalid characters, out-of-order sequences, incomplete croaks, and empty strings. For each of these cases, the function should return -1, as they represent invalid inputs. The algorithm's complexity is efficient, with a time complexity of O(n), where n is the length of the input string. This is because we process each character exactly once. The space complexity is O(1), as the stages array has a fixed size of 5, regardless of the input size. Let's walk through an example to clarify. For the input croak, we initialize stages as 0, 0, 0, 0, 0. Processing each character, we increment and decrement stages appropriately. See increments stages. 0 are moves a frog from stage 0 to stage 1, and so on, until k completes the croak and resets the stages. At the end of the first croak, all stages return to 0. Repeating this for the second croak, we track that the maximum number of frogs croaking simultaneously is 1. Thus, the result is 1. For invalid inputs, such as croak, the sequence is incomplete, so we return -1. This demonstrates how the algorithm handles both valid and invalid cases effectively. Here, we begin by defining a class called solution and implementing the function min_number_of_frogs, which takes the string croak of frogs as input. The goal is to determine the minimum number of frogs required to produce the given sequence of croaks. To achieve this, we initialize counters for each character in the word croak, C, R, O, A, and K, and also a variable max_frogs to keep track of the maximum number of frogs croaking simultaneously. As we iterate through each character in the input string, we increment the corresponding counter based on the character. For instance, when we encounter C, we increase the C counter and update max_frogs by calculating the difference between the current count of C and K, which represents the number of active frogs. For the other characters like R, O, and K, we also increment their respective counters. However, we include checks to ensure that these characters appear in the correct order of the word croak. For example, R should never exceed the count of C, as every R must follow a C. If it does, we return -1, indicating the sequence is invalid. Now, we handle two additional cases. If the input string contains any character other than C, R, O, or K, we immediately return -1, as such characters would make the sequence invalid. Finally, we ensure that all frogs have completed croaking, which means the counts for C, R, O, and K should all be equal. If this condition is satisfied, we return the value of max_frogs, which represents the minimum number of frogs needed. Otherwise, we return -1, as an imbalance in the counts indicates an incomplete or invalid sequence. This logic ensures that the solution is both efficient and robust, correctly handling all possible edge cases. Here, we begin by defining a solution class and a method called min_number_of_frogs. The input to this method is a string, croak of frogs, which represents the sequence of sounds made by frogs. Inside the method, we first set up counters for each character in the word croak, C, R, O, A, and K. These counters help us track how many times each character has been encountered in the string. Additionally, we initialize a variable max_frogs to keep track of the maximum number of frogs croaking simultaneously. Next, we iterate over each character in the croak of frogs string using a for each loop. If the character is C, it indicates the start of a new croak sequence, so we increment the C counter. At the same time, we calculate the number of active frogs by subtracting K from C and use math.max to update max frogs. Then, for each subsequent character in the sequence R, O, and K, we increment their respective counters. However, we also include checks to ensure the sequence is valid. For instance, there cannot be more R characters than C, as R must always follow C. Similar checks are applied to ensure O follows R, A follows O, and K follows A. If any of these conditions are violated, we return -1 immediately, indicating an invalid input string. Finally, if an invalid character is encountered, we also return -1 to handle cases outside the expected croak sequence. Now, after processing all characters in the string, we need to ensure that every croak sequence has been completed. For this to happen, the counts of C, R, O, A, and K must all be equal. This is because a complete croak involves one occurrence of each character in the correct order. If this condition is satisfied, we return the max frogs value, which gives the minimum number of frogs needed to produce the given sequence. However, if the counts are not balanced, it means some croak sequences are incomplete, and we return -1 to indicate an invalid input. This ensures the method handles both valid and invalid inputs correctly, providing a robust solution to the problem. To solve the problem, we begin by initializing counters for each character in the word croak, C, R, O, A, and K, all set to 0. Additionally, we have a variable max_frogs to track the maximum number of simultaneous croaks. Starting with the input string croak, we process each character sequentially. First, we encounter C, so we increment its counter to 1. Since there are no completed croaks yet, the number of active frogs is calculated as CK, which gives 1. We update max_frogs to 1. Next, we process R, incrementing its counter to 1 and ensuring that its count does not exceed C, which is valid. We then proceed to O, incrementing its counter and confirming it does not exceed R. Similarly, for A, we increment its counter and check that it is less than or equal to O. Finally, we handle K, incrementing its counter and ensuring it does not surpass A. This completes one valid croak sequence. The process is repeated for the second sequence, and at the end, all counters equal 2, indicating 2 completed croaks. The maximum number of active frogs at any point was 1. Thus, the output is 1. Now let's analyze an example with overlapping croaks using the input croak. Again, we initialize the counters C, R, O, A, and K to 0, along with max_frogs. First, encountering C, we increment its counter to 1. The active frogs are calculated as CK, which gives 1, so we update max_frogs to 1. Then, we process R, incrementing its counter to 1 and confirming it does not exceed C. Next, we encounter another C, so we increment its counter to 2. This time, the active frogs become CK, which equals 2, and max_frogs is updated to 2. Moving to O, we increment its counter to 1 and ensure it is less than or equal to R, which is valid. Similarly, A is increment to 1, remaining valid as it does not exceed O. Next, we process K, incrementing its counter to 1 and verifying it remains valid. Returning to R, we increment its counter to 2, still ensuring it does not surpass C. Then O is increment to 2, and its validity is confirmed. Continuing with the overlap, we process A, incrementing its counter to 2 and confirming that it does not exceed O. Finally, K is increment to 2, ensuring it remains valid as well. At the end of the string, all counters are balanced with C, R, O, A, and K equal to 2, indicating 2 completed croak sequences. The maximum number of active frogs at any point was 2, so we return max_frogs as 2. Now, consider the invalid input croak. After initializing the counters, we process the characters, incrementing C, R, O, and A to 1. However, the string ends before any frog can complete its croak since K remains 0, while the other counters are greater than K. This imbalance indicates that the input is invalid. As a result, we return -1. The time complexity of the solution is O(n), where n represents the length of the input string croak of frogs. This is because the algorithm processes each character in the string exactly once. The iteration is performed using a single for loop, which contributes O(n) to the time complexity. Within this loop, operations such as character comparisons, arithmetic updates to counters, and adjustments to max_frogs are all performed in constant time, or O(1), for each character. Since these O(1) operations occur for each of the n characters, the total time complexity remains O(n). Now, regardless of whether the string is well-formed or contains errors, the algorithm still needs to scan the entire string to determine validity. Therefore, both the best-case and worst-case scenarios result in an overall time complexity of O(n). The space complexity of the solution is O(1), meaning it requires a constant amount of memory regardless of the input size. This is achieved through the use of 5 integer counters C, R, O, A, and K to keep track of the counts of each character in the croak sequence. These counters occupy fixed memory, contributing O(1) to the space complexity. Additionally, the variable max_frogs is used to track the maximum number of active frogs at any moment, and it also uses constant space. Importantly, the input string crocofrogs is only read and not stored in any additional data structures. Since no extra memory is allocated based on the size of the input, the overall memory consumption of the algorithm is fixed at 1. A naive approach to solving this problem might involve explicitly simulating each frog's croak sequence using a data structure such as a queue or stack. While this method would work, it requires maintaining the state of each active frog, which results in n space complexity due to the additional memory required to track these states. In contrast, the current solution optimizes memory usage by focusing solely on counting the occurrences of the croak characters and enforcing their correct order. This eliminates the need for extra data structures, reducing the space complexity to 1. From a mathematical perspective, the time complexity remains n, because each character is processed once with constant time operations. The space complexity is 1, because the memory usage is fixed and does not scale with input size. This makes the solution both time efficient and space efficient, demonstrating its optimality for the problem. A common mistake when solving this problem is not validating the order of characters in the input string. For instance, sequences like croak or croca are invalid because they don't follow the correct order of C, R, O, A, K. Solutions that fail to enforce this sequence might incorrectly consider these inputs as valid. To address this, you should ensure that each C is followed by the appropriate characters in the correct order, and any deviation should immediately mark the input as invalid. Another frequent error is not accounting for overlapping frogs. For example, in a sequence like croak, multiple frogs are croaking simultaneously. If you aren't tracking these overlapping croaks properly, you might underestimate the number of frogs needed. A good way to handle this is by maintaining a counter or an array that tracks how many frogs are at each stage of the croak sequence. Lastly, some solutions assume a fixed number of frogs based on small examples, which can break down when the input has a large number of overlapping croaks. Instead, you should calculate the maximum number of concurrent frogs dynamically to ensure your solution is robust across all cases. Improperly handling edge cases is another area where solutions can fall short. For example, strings without any C, strings that contain extra or invalid characters, or incomplete sequences like crocro may not be handled correctly. To fix this, you need to explicitly check for invalid characters, ensure the string length is a multiple of 5, and confirm that all counters return to 0 at the end of the process. Another issue is inefficient state transitions. Some approaches use nested loops or repeatedly scan the string, resulting in higher time complexity. To address this, you can adopt a single-pass solution that leverages a state transition mechanism, such as an array or a hash map, to efficiently track the stages of each frog. This ensures that your solution runs in optimal time while maintaining clarity. When tackling this problem in an interview, it's important to understand its context. It evaluates your ability to simulate processes, manage state transitions, and validate constraints all at once. Think of each frog as an independent process moving through different stages of the croak sequence. For optimal performance, aim for an n time complexity solution with 1 extra space, or at most minimal space for counters. Brute force approaches with n squared complexity are unlikely to impress interviewers or handle large inputs effectively. This problem also provides an opportunity to highlight your skills in state management. Using arrays or hash maps to track and transition between states can demonstrate your ability to manage complexity efficiently. Additionally, always discuss edge cases during interviews, such as empty strings, invalid characters, or overlapping croaks. This shows attention to detail and helps you anticipate potential pitfalls in your implementation. This problem shares similarities with other string processing and validation challenges. For example, LeetCode 20, valid parentheses, involves validating sequences based on constraints, which is conceptually similar to ensuring the correct order in croak. LeetCode 921, minimum add to make parentheses valid, also requires balancing and counting elements to achieve validity. Another related problem is LeetCode 1249, minimum remove to make valid parentheses, which focuses on removing invalid characters to form a valid sequence. Lastly, LeetCode 316, remove duplicate letters, deals with maintaining order and adhering to constraints in string processing. Studying these problems can help you develop a deeper understanding of sequence validation and state management, which are central to solving the minimum number of frogs croaking problem. There are several approaches to solving this problem, each with its own trade-offs. The brute force simulation approach involves iterating through the string and assigning each C to a new frog, simulating their progress individually. While simple to implement, this method is inefficient for large inputs due to its O(n)² complexity. A more efficient option is using state transitions with array counters. Here, you maintain an array to track the number of frogs at each stage of the croak sequence, incrementing and decrementing counters as you process characters. This method achieves O(n) time complexity but requires careful attention to transitions to avoid errors. Alternatively, you can use hashmap-based state management. This approach dynamically tracks the count of frogs at each stage using a hashmap, offering flexibility to handle variable length sequences and edge cases effectively. While slightly more complex than arrays, it provides a robust solution that balances efficiency with adaptability. Great job! To recap, we tackled the minimum number of frogs croaking problem by simulating the sequence and optimizing the number of frogs required. We explored a hash map-based solution with linear time complexity. Remember to practice similar problems to strengthen your skills. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!